Hello, welcome to the training session for the Copernicus Marine Bio Black Sea. In this training session we will try to visualize some maps, sections and time evolutions of some of the variables available in the Copernicus Marine Black Sea catalog. This training is taking place into a Jupyter Lab environment. It is an environment which is on the web and which executes some Markdown language, and in our case it will be Python. So it means you don't need to install any software on your own computer. You can just run this exercise on the web once you have obtained a password and a login from Mercator-ocean International for Copernicus. I will first give a brief introduction about this exercise, then I will say something about the data we're going to use, about the software environment and the Python models we're going to need. I will propose 4 exercises, one with horizontal 2D maps, one with vertical profiles, one of some transects, so 2D vertical maps, and then a few time series. So the objective of this exercise is to use the Copernicus Marine Environmental and Monitoring Service, so abbreviated as CMEMS. So I will just say the Copernicus Marine, biogeochemical products, and visualize some of the typical coastal and open sea biogeochemical features in the Black Sea. And in particular, as I said just before, we will display some 2D plots, horizontal and vertical, and also some profiles and some time series. In this exercise, we will use the near real-time products of the Copernicus Marine catalog because they already use the latest naming conventions. After the next month of July and the new entry in service, the multi-year product will also use the same convention, so you will be able to use the exact same script as well for the multi-year products. Let's say something about the data we're going to use. So this example is based on the near real-time products for the Black Sea. And this code you see here, 007010, is just the catalog reference in the Copernicus Marine catalog for this product, so the biogeochemistry of the Black Sea. So this product, 007010, is the nominal product for the Black Sea biogeochemistry near real-time. And it's generated by 2 models, a physical model and a biogeochemical model. The physical model is called NEMO, and the biogeochemical model is called BAMBI. BAMBI stands for Biogeochemical Model for Hypoxic and Benthic Influenced Areas. And it's a model which is designed with the Black Sea in mind. It has 28 variables in the water column, including the carbonate system variables. And it also has a model of the bottom of the sea floor, which is called a benthic model, and this one has 6 variables. Something particular about this model is that it explicitly represents processor in the suboxic and anoxic layers. So the Black Sea is oxygenated close to the surface, but once you go deeper, you will find areas with very low oxygen or no oxygen at all. And some specific processes take place in these regions, and they are represented in the model. The Copernicus Marine catalog provides different data sets for this product. And in particular, you can find a lot of variables such as the concentration in chlorophyll, nitrates, phosphates, oxygen, carbon biomass of phytoplankton, net primary production, acidity, dissolved inorganic carbon, alkalinity, and you can also find specific 2D variables such as the oxygen on the bottom of the sea, partial pressure of CO2 at the surface, or the flux of CO2 between the atmosphere and the water. All the variables are computed on the exact same grid as the physical products, for which there is another training available if you're interested. And this grid has a resolution in the horizontal of about 3 kilometers, and in the vertical there are 31 levels. The products and the variables are provided as daily means or as monthly means. This little map, or this is a taken from the Copernicus Marine website. This is a little map of the Black Sea region, where you could see the Black Sea, the longitudes and latitudes around it. So these are the boundaries. This is the Sea of Azov, which is not currently taken into account in the Black Sea model. And the Black Sea is composed of a deep part, which we call the open sea, with depths up to 2,000 meters, and of the shallow northwestern shelf, which is here and has depths of maximum 200 meters. So the processes, the physical and biogeochemical processes, are very different in between these two regions. And the shallow northwestern shelf is very strongly influenced by rivers. In this area you have the delta of the Danube River, whereas more to the north we have the Dniester and Dnieper rivers. On the Copernicus Marine website we find some more information about this product, among which the variables available, which I already mentioned, the resolution, the vertical resolution, and the time availability of the product. The data and the variables are available in a format which is called NetCDF, or NetCDF4 for the version 4, which is a very common format in atmospheric and oceanographic sciences. It's a binary format, and libraries exist to read and write to this kind of files in a whole lot of different softwares, among which Python, which we're going to use for the current Jupyter Notebook. You can find more information about this product on a dedicated product page on the Copernicus Marine web portal. You just look for the Black Sea and then for biogeochemistry. There's also a product user manual, or PUM, and also a quality information document where you can find information about the validation of the model product compared, for example, to observations realized in situ or by satellites. All these documents you can download from the Copernicus Marine website. And then if you want to download yourself data from the website, you just have to remember that you're using the product 007010, or you can just look for the Black Sea and then you will automatically find it. You can choose which data sets you're going to use. For this current exercise we're going to use the phytoplankton and nutrients data sets, but there are more. We're going to use for this exercise the monthly files, which take the monthly mean of the variables, but you could also just take daily means. These are the latitudes and longitude limits of the files for the current exercise. So this is the whole Black Sea, but you could also download just a smaller part of it. We download two time steps, one on the 1st January 2019 and one of the 1st of September 2019. We downloaded them by FTP, and this gives us about 40 megabytes of files. Of course, when you download them yourself, you could choose different settings for all of these. The files we already downloaded are stored in a subdirectory which we called data, in this case of this exercise. If you want to download the data yourself, you could do so from the CMEMS website, from the Copernicus Marine website. You just have to obtain a login and password. So these credentials are of course free, and there's a tutorial how to obtain them and then how to download the files you want. Something about the software environment. So we're going to use a Jupyter Notebook, which is a file containing both text and executable code. The code is executed on the server, so you don't need to have anything on your own computer. You access the Jupyter Notebook through your website, to your web browser. And in the case in the case you want to modify the command or do something different, then you would have to install yourself the software. So the code itself is going to use the Python language. And the Python language is a basis upon which we can add some modules. In our case, we're going to use different models. And the first one is OS. It's an interface with the operating system. And then we have some modules about mathematics and arrays, and some models used to generate the plots, and more specifically geographical plots with maps. There's another module which we're going to need. It's the NetCDF module used to access the binary NetCDF files. In this Jupyter Notebook, you have some buttons on the top of the notebook, and the ones which we're going to use the most is this one, where my mouse is now. It's like a play button, and it executes the code inside of a cell. So this is an example of a cell. If I click on this cell and then click on the play button, you see it will execute the contents of the cell, and it could sometimes give you an output. If an output is provided by the command, then it will be displayed just below the cell. So this command was just to execute the Python and check which version is currently installed, and in our case it's Python 3.7.3. If you want to install all of this on your own computer, then a convenient way of installing Python and the modules would be to use Anaconda. And if you look on the web for Anaconda and you install it, and then you could use Anaconda itself to install the further tools you need. For example, you could use this command, conda install Python 3.7, to install this version of Python. And then you can also use conda to install all the required modules. You just type conda install and the name of all the modules you want to install. If you don't like Anaconda, you can also just install Python from the web, and then you could use, for example, pip, which is the Python module or package manager, to install all the required modules. If you're going to work inside of the Jupyter Notebook, if you change the modules, if you install new modules, then you have to restart the kernel. So the kernel can be stopped or restarted from this menu here on top of the screen. Okay, so I will go forward and suppose that you have all these modules accessible. They are accessible immediately if you just run the Jupyter Lab notebook, or if not, I will suppose you have installed them on your own computer. Once these modules are installed or available, then you still need to import them into your current environment. So this first cell here gives you, it's a command to ignore some of the warnings. So we execute it, and this particular cell doesn't generate any output. The next one imports all of the modules we just installed, and again this cell doesn't generate any output because there was no error. If there was an error, then it would be displayed below here, underneath the cell. So probably the only possible error would be that it can't find the modules you try to import. In this case, you just have to install them again, and then rerun this cell. The next cell here is just an instruction to save 07 and 03 inside of the variables region code and NB code. So if you remember, 07 is the code for the Black Sea, and we're going to use it a lot, so we save them into two variables. Again, I push this play button here, and the code is executed, and there is no output. The next thing we will do is to create a function, a Python function. So we just, at this stage, we just define the function. We don't execute it yet, and it's a function that's checking if a particular folder or directory exists on the disk. So if we provide a certain name of a certain, folder, then this function calls the operating system function to check if the folder is actually existing or not. So when I click on the play button, it just creates this function, and it will now be available to subsequent cells. The next cell is another definition of another function, which is checking ranges. So let's define this function as well, and let's store some more variables inside the environment. If we put together the two variables 07 and 03 into a single string that we call xcode, and then we define two paths, so two folders. With the first one is the data path, which is the concatenation of data and the previous variable. So it will be data 0703. And the output path is where we will store the results of our exercises. We will do just in a few minutes. It's the directory out and then 0703. And then we can use the function which we defined just before to check if these directories already exist, and if not, they will be created. And of course, if you're working in the Jupyter lab, they are already existing, and the data path actually already contains the files that we will need. They are already downloaded from the Copernicus Marine catalog and saved there for you. So let's run this cell as well. There is no output because there doesn't need to be any. And then we will now use another code to check what's inside the current directory. The dot here is just the code for saying the current directory, the one we're in now. So let's look what's inside. And we have these files. The first one is the Jupyter Notebook we're running now. Then we have a subdirectory called data, another one called docs, images, and out. And now let's check what's inside the data subdirectory. So remember, data path is just a variable containing a string of characters, which is data. So this is this data directory, and let's check what's inside. You can see there are a certain amount of files inside of this directory, and the file names are interesting because they tell us what the file is about. The first part here is the date for which the file is relevant. So you could see this first file would be relevant for the day 15 for the month September of 2019. It's a monthly file. So it's the mean of the September month, centered on 15th of September. The next part of the file name is the producer of the file. So in this case, it's the University of Liege in Belgium. The dataset is the phytoplankton. The models are used to create it are Nemo and Bambi. It's about the Black Sea. The file was generated on the bulletin date of 29th of October 2019. It's an analysis. And this AN in other cases could be FC, which would mean it's a forecast. So something relevant for the future. And then this is the version of the dataset. And you could see in our case, in the data directory, we have files for September, but we have also files for January. We have files for the phytoplankton, for the nutrients, for the biology datasets. And this one is a file that you can download from the CMEMS website, for the Copernicus Marine website, by using what's called the subsetter, which allows you to download files for just a specific subregion, or for example also concatenate different files for different days or different months into a single file, which will be automatically generated for you. And this is an example of such a file. Okay, so I hope this long introduction about the data files we're using and the code we're using is clear for you. And if it is, we can now start with the first exercise. The first one is about horizontal maps or horizontal plots. And we're first going to define an amount of variables, and then we're going to use all these variables together to generate the plots. So first we're going to tell the Python environment here which files we would like to use. So we just define 3 variables, which will contain file names for each of the relevant datasets, the nutrients, phytoplankton, and biology datasets. And for each one of them, we're going to define one file in January and one file in September. And after that, we will use this variable, nutrients netcdf. We could give it any name we like, but we chose to call it nutrient netcdf, which will just concatenate the path, so data, and then the file names. So let's run this cell. There it is, there is no output, and then if we, in another cell, we ask the contents of the variable, there should be an output, and yes, there is. It's called data 0703, and then the name of the first file, and the same thing for the second file. And now we're calling a function from the netcdf module, which we imported before, and if we do that, it actually opens the file names and reads the data sets. We're still going to define a new variable, which we call j, and we will just use it to tell if we want to look at the file for January or the one for September. So 0 will mean winter, or the file for January, and 1 will mean summer, or the file for September. There it is. Let's look at the nutrients dataset, the one containing nitrates and phosphates. There's a function called .info, which gives us information about the contents of the netcdf file, and then it displays some information it just read inside of the netcdf files. So the first thing we have are the dimensions. So the netcdf file basically contains a grid with one index is about longitudes, another about latitudes, another about depths, and another about time. And you could see what's inside of all these indexes and the ranges, the actual values. For example, you could see depths. The first depth is 2.5 meters, then 7.5 meters, etc., up to 2,140 meters depth. After the dimensions and the coordinates, we find some information about the variables actually contained into the file. Here we have two variables. One is nitrates, the other one is phosphates. And you could see it's a 4D grid, a grid with 4 dimensions, with the indexes are longitude, latitude, depths, and times. There are also a number of attributes, which are text information about the contents of the file, which you could read and gives you information about different things. So in this cell, we will just ask Python to display us the variables, and again it gives you this information. The coordinates are displayed in the next cell, and you could see that in this case the nitrates and phosphates depend on 4 coordinates, 4 dimensions, among which the depth. So this means it's a 3D dataset plus the time dimension. If you would like to check out other comments you could have about NetCDF datasets, you can just type yourself the name of the variable containing the dataset. Also add the time, and then, for example, we could ask the depths of the dataset. One line is enough, and then just push the run button, and it will give us all the depths available. If you click on these little cylinders here, you could see all the depths, so 2.5 meters, 7.5, 12.5, etc., etc., going down all the way to the bottom, about 2,140 meters depth. We could do the same thing for the other data sets, so we just checked the nutrients, but there's also phytoplanktons. If we ask to execute this cell about information, it gives us the same kind of information, but for the nutrient data set. Again, we could use another command to check out which variables are inside. Here in this case it's the chlorophyll and the carbon content of the phytoplankton. We could ask again the coordinates of the file. We could ask again the same thing now for the biology data set. In this case we have one variable giving us the oxygen content of the water, the oxygen on the bottom of the water, and this is interesting because it follows the bottom for you. So the bottom, of course, is at a different depth for each coordinate in longitude and latitude, and this variable just extracts all the oxygen concentrations at the relevant level, vertical levels, and assembles them into a 2D map. And this variable is the net primary production in the volume. So for each grid point in longitude, latitude, and depth, and in time, if you have multiple time steps, it gives you the net primary production. Let's go to the next cell. It's the same thing again, but for the biology dataset, it gives you the name of the variables. It gives you the coordinates used, and you could ask any other field of this dataset. If you type in a cell the beginning of a command or the beginning of a variable, in this case bio dataset at the time j, which is now winter, I guess, and then you press the tab key from your keyboard, it will show, it will propose to you to complete it automatically. And then you see all the fields you could ask him to display. For example, chords we already used. Let's execute this cell, and it gives you the coordinates. Now you learned how to read different things about the datasets. Now let's define some more variables, and then let's finally go to plotting the dataset. We will give some names to some variables, like the long name is a variable containing the name of the longitude variable, which is just longitude. The same for latitude, for time, and for depth. So it's nothing very spectacular, we just define some strings. We could give we could save the name of the datasets into some more variables. The name of the chlorophyll variable, for the chlorophyll variable, is just CHL. for the oxygen, for the nitrates, for the phosphates, for the net primary production. You could save everything you want in any variable you want. For this exercise we will use these names. And then let's go to setting the variables we need for actually plotting. So for the first plot we will choose to plot it in the winter. So we put j equal to 0. We can choose which variable we would like to plot. So here you have 3. If you execute these 3 lines, it will execute the first one, then the second one, then the third one. The second one will overwrite what you did in the first one. So in the first one you put the value of the nitrate name into the variable you selected, but then you put the chlorophyll into this variable, and then you put the oxygen. So in the end what you end up with is just the oxygen, and the 2 first lines are actually useless. But if I comment out the second and the third line, then of course the nitrate name will be inside of the variable we selected. Here the same thing for some selections of the range of the plot we would like to see. So for the nitrates I would like to plot the values between 0 and 30. You could also specify none, and then we'll see what it will do. Actually it will find the range thanks to the minimum and the maximum value inside of the data. Here we say that we don't have a 3D dataset, but then if the variable actually has a depth coordinate, then it will be put to true. Here again we just set up some names, some variables which we will use in the plot. You could choose to plot a specific area by selecting yourself the longitude and latitudes you would like to have in your plot, the minimum and the maximum of them, or you could just do it automatically by choosing the minimum and the maximum of the variables. So this will plot from the minimum available latitude to the maximum available latitude, and the same for longitude. You could also choose the depth. If you are going to plot a horizontal plot, it could be the surface at depth 0, but it could also be at 100 meter depths or 1000 meter depths, whatever you like. So I now run this cell, and it doesn't need to generate any output, and then we arrive at the cell which will in the end actually plot something. So this one is giving you the size of the paper size, if you like, of the plot. We choose the projection, in this case Mercator projection. We give him the longitudes and latitudes ranges we would like to plot. So these variables were defined just before, if you remember. We give him some cosmetic instructions like the name of the axis, longitude in degrees and latitude in degrees, etc. The range of the ticks on the label, on the axis, the colors we would like to use, the fonts we would like to use, etc. So these choices are just cosmetics. It's not very critical for our exercise. The ranges, we just defined the ranges before. Now we're going to use them to say which ranges he needs to plot. And then for each of the times we want, so in our case it's just the winter, we are going to in the end actually plot it. So this command is opening a figure. It's going to use the map package to show you a pretty geographical plot, and we're going to do some colors, the contours, with the ranges we defined before, between the minimum and the maximum and the step we chose before. Okay, some more instructions to have a pretty plot with the right meshes. We're going to plot some horizontal and vertical, so longitude and latitude lines parallel to meridians and parallels every five. There will be 5 lines from between the minimum and the maximum. More instructions about these meridians and parallels, more instructions about the colors we want to use, and these 2 lines are using the packages the Python modules we imported in the beginning to draw the countries and to fill the land, because of course we have values just in the sea, but we want something pretty also in the land. If you don't like this way of filling the land, there are others available. Blue Marble, Etopo, etc. So in this case you comment these lines and uncomment another one here. We could try it immediately. Let's just first go with the standard one. More cosmetics. Here we set the title of the plot, we draw the labels, and here we choose to save the output file inside the folder defined in the variable auth_path. So maybe you remember this is just out and then 0703, concatenated with the file name and an extension PNG. And here we define the file name and the directory. Here we actually save the plot inside of this file. And then we also show the plot, and when it's done we close the plot. So let's do it. Let's execute this whole bunch of lines of Python code. Hopefully it will generate a figure. And there it is. This is the figure we asked for. So it's the nitrates. It's in winter, in January. It's at the closest depth to what we chose. So we chose 0 meters, the surface, but actually the uppermost layer, is 2.5 meters depth. And it's showing us the nitrates into the seawater. Here you have the longitudes we chose, the latitudes we chose, and the color bar we chose. And you can see the land borders. So this is Romania, this is Ukraine, etc. And finally, what does the map shows us as an interesting oceanographic feature or processes? You could see that the concentrations are very high on the northwestern shelf, and in particular in the region where the Danube is flowing into the sea. So the Danube has a delta here on the border between Romania and Ukraine, and some more mouths here, more to the south. And also the Dnieper and Dniester rivers, which are flowing here, yield very high nitrate concentrations. And then the general circulation is propagating, is affecting this nitrate all along the coastline, and you can see it up to here. You have some other rivers which are a lot smaller, like the Rioni here. Okay, so if you're interested in other variables, we can go up. Let's go up all the way to where we chose the variable. So in this box here, and let's uncomment the line for the phytoplankton. Or no, let's uncomment the line for the oxygen. So now this variable, which is called var_cell, will have the nitrates, and then it will immediately be overwritten with the name of the oxygen variable. So it would be, we could comment this line, but it would be yielding exactly the same result, because anyway it's overwritten by this command. And let's choose some pretty values for oxygen. So if you don't specify anything, you could choose none and none, like this. And then it will plot between the maximum and the minimum available, which are 0 and 330. But actually there's nothing much on the surface of the Black Sea. There's nothing much of a 0 oxygen concentration, and we chose a prettier minimum to 260 millimoles per cubic meter. So now we changed this. Let's run the cell again. There it is, no output for that one. And then let's generate a plot by running the next cell. And now we should have the plot of the oxygen. We didn't change the layer, so it's still the surface. And you could see now the title changed and the content changed. We have the color bar between 260 and 330. And we can see that there's a lot of oxygen on the northwestern shelf in winter, about 300, 330. With high concentrations, and then it's a little bit less, like 310 maybe in the central open sea. Let's plot with another map. Let's comment these two lines, and let's uncomment this one, for example, a topo. In Python you have to align the code, so you could see all the line starts at the 7th, or I don't know which character. If this one is not at the right place, let's execute the cell. Then you see there's an error generated in a red box between the cell we just executed, and this is an error which says unexpected indent. So it means one of the lines into your cell is not starting at the right place. So this one I just uncommented, but I didn't put it at the right place. So I will now align it with the other ones, like this, and execute the code again. And this time we don't have an error, we have an actual map, and you can see it's the same map as before, but just now the land is filled with a different method. Okay, so that's the exercise for the 2D horizontal plots. You could try different things, you could try different variables, you could try to plot a subset, you could try to change the color bar, you could try to change the aesthetics of the plot, and then when you're happy with it, you can always find the result in the subfolder out. You have all the PNG files containing the plots you generated. Let's do another plot. The Black Sea is a very stratified sea, so you have a lot of, especially if you look at the biology, you have a lot of different things going on close to the surface and then in the deeper layers. So let's look, for example, at oxygen. How is oxygen behaving, and also plankton? We go to exercise number 2, and the question we want to answer with this exercise is how vertical profiles of oxygen and pH or plankton or whatever look like in the Black Sea. Let's look if there's a stratification, if there's a gradient, a vertical gradient, etc. So we're going again to define a lot of variables, and then we will run some commands to actually plot what we want using all these variables. If you want to plot a vertical profile, you have to tell him which one. So we arbitrarily choose to plot the vertical profile of oxygen at the latitude 43 and the longitude 32. So if we go back to the horizontal map, latitude of 43 would be here, and the longitude of 32 would be here. So it would be somewhere here. We will plot what's going on in the vertical at this particular point in the Black Sea. And this is of course a part of the deep region, so we will have values up to almost 2000 meters if we want to. So we run that cell. We run also the next one. Let's look at winter for a start. So I delete the 1 and put a 0 on there. And we're going to extract the phytoplankton values and the oxygen values at that point and at that season, so the file for January. And then again we define some plots, we define the depths, we use the data we just extracted from the netcdf file. We choose some colors, so if we're going to plot two variables, we choose two colors. We again have a lot of cosmetic choices to make. The axis, the depths, the values we want, the sizes, the fonts, etc., etc., the titles, and then again the file where we're going to save the results, and we ask Python to show us the plot and then to close the plot. So let's run it, and here you have the result. This is phytoplankton and oxygen. So the horizontal axis here is actually the vertical axis in reality, is the depth with the surface here at 0, and then you go all the way down to the depth at that particular point we chose. The red curve is the oxygen, and you have the scale on this axis, and the blue one is the phytoplankton, and you have the scale here. So you could see in the surface we have 310 maybe, something we saw also in the horizontal plot, and then it goes to 0 quite quickly. So as I mentioned before, at the surface a lot of oxygen, but around 100 meters depth maybe already there's no more oxygen, and all the rest of the water column is completely depleted of oxygen. Phytoplankton also has a kind of large value at the surface, and then it goes to 0, and all the rest of the basin is completely free of plankton, of phytoplankton. Now let's go back and back more to the previous cell, and let's look at what's happening in summer. So I go to the previous box and I chose, where is it, season index here. I put it to 1. This is going to, the effect of this is going to be that we read the file for September instead of reading the file for January. And then I plot the data, and a new plot is coming. And you could see now at the surface, so at the surface the oxygen is now a lot lower, 260 maybe. This is of course related to the temperature of the surface water and the solubility of oxygen as a function of the temperature. And for the plankton, we have also a lot less carbon mass of phytoplankton, and you could also see that we have subsurface chlorophyll maximum or plankton maximum. So the value is actually lower at the surface, then it increases at about 50, 60, 80 meters, and then it decreases to 0, and all the rest of the column has 0. So this is what typical profiles look like in the Black Sea. Now, instead of plotting just a profile at a single point, we could again plot a 2D plot like the first one, but instead of plotting a horizontal map, we can plot a vertical map along a longitude or a latitude, whatever you choose. And in this case, we choose to plot the depths from 0 to 200 at a certain latitude, 43, the same as before, and for all the longitudes, so for 27.5 to 42. Let's run this cell. No output because we just assigned some value to some variables. And then it's the kind of same thing as before. We're going to choose to plot something in winter. We read the data sets. We set a lot of variables to choose everything we want, the longitudes, the latitudes, the depths. And you can see the depths are going to be from 0 to 200. We define some variables that we could plot later. The minimum and the maximum for the color bars, etc., etc. Let's run this cell. If you want to, you can always ask to see the value of some variables you set. So in this case, the depth selection variable contained all the depths. And if you just put the name of the variables, then you have the output coming just below the cell. If you click on these little cylinders, you see the actual values. So in this case, we have the values from 0 to 200, which is what we chose, but there is no level at 200. The level immediately above is at 170 meters. So we're going to plot everything between 2.5 and 170 meters depth. Now we're creating the grid. The grid is now depending on longitude and on depths. It's not depending anymore on longitude and latitude. All the cosmetics for the plot are here again. So I think you get the idea, so I will just skip it and execute the code without wasting any more time. And then we actually come to the cell where we plot the figure. So it's opening a figure, choosing the right time steps, creating the grid, using all these variables we defined just above, and doing the plot and then saving it into the PNG and showing it on screen. And it gives you this plot, which is supposed to come now. Oh, I'm sorry, this is not actually plotting, it's a function. We see here, we define a function which is doing the actual plotting, but we are not calling the plot transect function, we're just defining it, and we will call it later. So now we define this function, and we are going to call the function to plot it. So let's execute some more. So here it again explains what we're going to do, but you already know it now, and we call here, in the end, we put the chlorophyll into the data, and then we call this function with the variable data, which is chlorophyll, with the other variables we set before. And if we execute that cell, then we finally get the plot. So you can see here, this is the westernmost part, close to the Danube mouths. So this box is a little small, but whatever. This is the surface. This is the maximum of the phytoplankton and of the chlorophyll you saw into the vertical profile. So you remember that you have a maximum a little bit deeper, but you can also see that here you have a kind of light blue, which is not 0, right? So on the surface we have something like 0.5 maybe milligrams per cubic meters or micrograms per liter of seawater, and yes, that's about it. In the deepest part of the sea you have 0. And now if we want to plot in summer, it's exactly the same, except we put chlorophyll with a time index 1 instead of the time index 0, and we don't have to redo everything because everything is defined in the function. So we now just call the function a second time, and here we go. It should give us the same, but for the summer. So you can see here that in summer all the nutrients are consumed. You don't have this huge peak of nutrients in the Danube region anymore. You still have a deep chlorophyll maximum, but you have a very low values also above. And of course you have 0 below of the deep chlorophyll maximum. So the situation in summer is really different compared to the one in winter. Okay, let's go to the last exercise for this training session. We will now look at the time series. It means we will extract some values or build some values somehow from multiple time instance of the files. In this case, we use the Copernicus website to generate, to subset, using the subsetter to subset a part of the time series. So we chose different monthly files, one after another, and the Copernicus website assembled them for us into a file where the time dimension is not a singleton, it has multiple instances. And let's look at the CO2. Let's look at the partial pressure of CO2 at the surface and also the flux between the atmosphere and the sea, which answers the scientific question: is the Black Sea a source or a sink of CO2 for the atmosphere? Is it contributing to increasing CO2 concentration in the atmosphere, or is it the contrary? Is it absorbing CO2? And in this case, this is the data we extracted from the CMEMS catalog. So I told you we would take monthly files, and actually we take them from the 1st January 2017 up to 2020 monthly files. And this gives us, the subsetter gives us a file of about 24 megabytes. But we saved it already for you into the data subfolder. And you are now familiar with the procedure. We will define a lot of variables and then use all of them together to realize the plots. Here we just tell him the name of the file. The file is joined together with the name of the directory into this variable, and then this variable is used to open the NetCDF dataset. Let's run the code. There's no output. Let's see what's inside of this dataset. And here's an output. We have two variables: the partial pressure at the surface and the flux between the atmosphere and the sea. And now we're going to take the spatial mean of this variable. We're also going to plot the variable into a single point, but for the first exercise we're going to take the spatial mean. And to do that you have the function mean. And something we need to be careful here is that if you take the mean over the whole domain, the points in the land have the mathematical representation of not a number. So the points in the land are not a number, and they will be skipped due to this instruction when the mean is computed. So the mean is actually computed over all the longitudes and all the latitudes, but by skipping the points in the land. So we get the CO2 partial pressure only over the sea. There we go. There's no output because it just computed this mean and then saved it inside of the variable CO2 mean. You could see that it takes the average over longitudes, over latitudes, but not over time. So instead of having a 3D variable, we now have a 1D variable where the single dimension is time. And at each instance of time, we have just a single number, which is the mean over longitudes and latitudes. And now we have this code which you already seen before. It's choices we make about which variables to plot, which colors to use, fonts, axes, etc., etc. And then we plot actually the figure, and we save it to a PNG and we show it. So let's go. And this is the output you get. The red curve is the partial pressure of CO2, and you could see it oscillates between something like 32 and 50 microatmospheres. And the blue one is the flux between the atmosphere and the sea. And you could see it's sometimes above zero, sometimes below zero. When it's positive, here, like here, or here, or here, it means the CO2 is actually going from the atmosphere inside of the sea. When it's negative, it's the contrary. So the sea is actually emitting CO2 inside of the atmosphere. And you can see there's an annual cycle, and it is not the same every year. So you have years where more CO2 is going into the atmosphere, and other years where less CO2 is emitted. This was the mean over the whole basin. But we could also arbitrarily plot the time series for a particular arbitrary longitude and latitude. This is what we are going to do in this very last part. So we choose one point, we extract the data set from that particular point. In all the exercise we did before, when you extract some values, you can choose a method, and what we choose is just the nearest point. So this is why when we chose to plot something at 0 meters depth, we obtained the plot at 2.5 meters depth, because it's the nearest value. You have other methods as well. So let's go to the next one. Here we again plot exactly the same thing as before, but instead of having the mean, we now have the values at that particular specific point we chose. And you see you have a similar plot, except it's much noisier, because you lose the averaging effect of the previous plot. But again, anyway, you have sometimes negative values, sometimes positive values, meaning that depending on winter or summer, on the seasonal cycle, the Black Sea is sometimes acting as a sink and sometimes as a source for CO2 for the atmosphere. So thank you very much for watching this training for the Copernicus Marine Black Sea Biogeochemistry, and I hope you enjoyed it and you learned something. Bye bye. Thank you.